All right. Probably we'll get started. Uh, Shubham, thanks for joining. We will get started now, and maybe more people will join as we go forward. Okay. Um, so before, so this week is going to be about gear turbofan engines, and we'll be solving one problem based on gear turbofan engine. So before I get into the problem, uh, do you have any doubts, Shubham? Do you want to have a do you want to ask any quick questions? I will be able to take now. Okay. For some reason, I'm not able to hear you properly. If there is any problem, you can even use chats to ask your questions. All right, Shubham. Thanks. So, um, anyway, you can, if there is any doubts, if you come up if you face any doubts while I'm doing this, while I'm solving this problem, you can stop me anytime. And also, I will be completing this problem in another 30 minutes or so. So after that, also, I will be available to take your questions. All right. Um, Again, I welcome you all for this seventh problem solving session for this of this course, Aeroengine gas turbine cycles. And this week, week seven, we covered gear turbofan engine, two spool gear turbofan engines. We have been studying turbofan engines for last 2 weeks, and in continuation, we are also studying this week gear turbofan engine, and we will also be studying about turbofan engines for another 2 weeks. And turbofan engines being used widely in different aircraft engines for different purposes. So that's why there's a much importance is given to turbofan engines, uh, even in this course. So basically for a gear turbofan engine, we again saw two kinds of configuration like we saw in week 6. We have uh, fan and low pressure compressor in the same shaft as low pressure turbine, and high pressure compressor with the high pressure turbine. And the other configuration is fan is ran by low pressure turbine, and compressor is ran by high pressure turbine. Uh, so these are the two configurations that we already saw in two spool turbofan engines also. In addition, what we have is we have a set gearbox between the fan and the low pressure compressor. Or basically, you can say the fan is driven with a lower speed, and the speed and torque is achieved by installing a gearbox in one of the shaft. Okay, and we also saw the performance of it. That's what we studied in week 7. Let me give you a quick recap of how this engine looks. So this is one such configuration. I didn't show the other configuration. So in this configuration we have uh, so in this configuration we have what do you call fan, uh, and we have compressor. In between you will see here is a gearbox. So this thing is a gearbox, right? And what we see is there is a shaft going on. This what do you call, a light blue grayish color shaft which runs from low pressure turbine to which runs from low pressure turbine to low pressure compressor, and from there also you have a small protrusion which is running the gearbox, and at the end of other side of the gearbox you have fan. Okay, basically the compressor and fan is rotated at different speeds. That's what. So these are the common knowledge we know at this point of time. Again, we have two separate streams: fan and bypass stream and core stream. In core stream, again it goes through compressor, low pressure compressor, high pressure compressor, then chamber, combustion chamber, and then turbine, and then nozzle. So construction wise everything is same. Only thing is we are rotating the fan at a different speed. That's all. Um, and the reason is we all know. Uh, so the main reason is we want a higher. Uh, so the whole point of going into gear turbofan engine is, let me give you a slight context so that you will not forget the reasons behind developing such a engine. So the reason to go to gear turbofan engine is people were exploring how do I increase the efficiency of this engine, or how do I decrease the specific fuel consumption, and the only way is to increase the bypass ratio. But if I continuously increase the bypass ratio with the conventional turbofan engines, you are going to face a lot of issues, because bypass ratio increase leads to increase in diameter of your engine, and increase in diameter leads to fan tip velocity to be very high. And if it is going to supersonic, there's going to be shock and aerodynamic losses is going to happen. And all these reasons is restricting you to go towards high bypass engine, high bypass ratio engine. Only thing is you want to rotate your fan at a lower speed. And and how are we going to match that low speed fan to the low speed, high speed, low pressure compressor? Is via this gearbox. So that's when people came up with the gearbox. Like, okay, let's add a gearbox so that we will reduce the speed of the fan. And when they do it, they were able to go and reach a much higher bypass ratio. And that is what is going to when they go to when they get higher bypass ratio, they are going to get higher efficiency. And that is exactly the problem that we are going to solve today also. um, it is going to be an extension of one of the problem we solved in the lecture. Okay. Just to show why the gear turbofan is efficient. I mean, what is the main reason to go towards gear turbofan, and how you should take it with a pinch of salt. For the same bypass ratio, your gear turbofan is going to um, perform lower than a conventional turbofan. But the main reason for to do gear turbofan is to go for a high bypass ratio. So you cannot directly compare at the same bypass ratio. You cannot compare two turbofans. That will lead to misleading results. Okay, uh, that is something I want to make sure that you understand. Anyway, we will revisiting this again and again. So as usual, we'll just go through the TES diagram of this turbofan engine. This is going to be same as, so thermodynamically there is no difference, right? Mechanically your fan is rotating at lower speed, that's all. But there is going to be pressure rise across fan, compressor. There's going to be temperature increase across the combustion chamber, and turbine is going to give the work. All these are remaining same. There is no I mean, as the thermodynamically, the TS diagram is not getting affected. So you can see from P infinity you have P02, which is the inlet pressure rise, and from 2 to 3 you have fan, again there is a pressure rise, and from 3 to 4 you have a compressor. So now you are getting into core stream. There is again a pressure rise, low pressure compressor, and then you have a high pressure compressor. This will be your highest pressure in your in your engine. And at the end of the high pressure compressor, the air enters the combustion chamber, and in the combustion chamber you are adding fuel, so your temperature is supposed to rise, and because of combustion. And during this process there could be some losses, so that's why P05 will not be equal to P06. So the station numbers are a little bit different than a two spool turbofan engine, so please note that. Okay. And 6 to 7 you have high pressure turbine, and 7 to 8 you have low pressure turbine, where the gas is continuously expanded to 8. And from 8 to 9 you have jet pipe, and in the jet pipe you have less losses. Okay. um, and then you have nozzle. 9 to 10 is the nozzle, this is the core engine nozzle. And also now you come to the bypass stream. In bypass stream from 2 to 3 you have already pressurized the air. Now it is going to 3 to 11 it is going to expand in the nozzle, so that will be over here. Okay. So This is your entire TS diagram, same as two-spool turbofan engine. Just the station numbers is bit different. Okay. Mm, yeah. So the the question that we have here is, you can see, um, it's a turbofan engine question which we already solved in the week 6 lecture, if you look at it. So for this configuration where fan and low pressure compressor is connected to a low pressure turbine and the high pressure compressor is connected to high pressure turbine. So this is the numerical that we solved in the week 6. And but only change is this bypass ratio. We solved it for 9. Now we are going to solve it for 14. And the gear ratio is, we additionally have gearbox with a gear ratio of 1:4. Okay. Which means the low speed, um, the speed of the RPM of fan divided by the RPM of the low pressure compressor, or RPM of the low pressure turbine, will be equal to uh, 1 by 4 basically. Okay. So which means it's a 25% speed is the speed of the fan. Okay. And you have low pressure compressor pressure ratios and high pressure compressor pressure ratio, which is 2.47 and 12. Fan pressure ratio is 1.36. Turbine inlet temperature is 1600 Kelvin. And core engine mass flow rate is also given 138 kg per second. So we need to find out all the parameters that we are interested in. Example, the velocities, area of the nozzle, um, you know, the thrust TSFC, and efficiencies. Since it is going to run at sea level, we do not have propulsive efficiency and overall efficiency. By now, I think you are all familiar with that. Yeah. So these are the given data, and we also have efficiency. So one thing you should note here is you have additionally gearbox efficiency. So you have some mechanical efficiency with the gearbox. So it cannot 100% transfer the work. Instead, it can transfer only 98%. So that those are the two additional changes. So first let's look at, let's say if you don't have gearbox with the beta equal to 9, this we solved in the lectures. You can refer to the notes of week 6. And these are the parameters that we got from these are the solutions that we got from that problem. So you were able to obtain a thrust of 360.56 kilonewtons, and your TSFC is around 0.0087 grams per newton second, or you can also write it in terms of kilonewtons per second, which will be 8.7 grams per kilonewton second. Okay. Now the thermal efficiency is 37.48 percentage, and propulsive and overall efficiency is 0, that we already know. So let's go forward and solve for the geared turbofan with the bypass ratio of 14. Okay. So in this case, if you think about what has changed, okay, so let me just quickly give you a hint how we are going to solve. We have inlet, and inlet we are going to get P02 and T02, and then we have fan, and then you have low pressure compressor to get and the low pressure compressor pressure ratio is 2.47, and then you have high pressure compressor and its pressure ratio is 12 is also given, and then you have combustor T05 is given 1600 Kelvin. Based on that you can find the uh, fuel air ratio. uh, Sometimes you will be given fuel air ratio and you'll be asked to find the turbine entry temperature. And HP compressor and HP turbine is in the same shaft, so you may need to use that work to find out what would be the exit pressures and temperatures of turbine. And then LP turbine, LP compressor and fan are in the same shaft, but only thing is in this place you have a gearbox, that's all. Okay. But yeah, as I said, thermodynamically there is no much of a difference. Only thing you need to take into account is the efficiency of the gearbox, because this work is not fully transferred to fan. There's a 98% efficiency is what is fully, 98% of that is only transferred to the fan. So, and then you have tailpipe. For this case we are assuming no losses. and then you have a nozzle, and nozzle we can find pressure, temperature, and velocity, and that will be useful for finding the thrust area of the nozzle and TSFC. Okay, and then in the bypass ratio you have fan, and similarly you can find pressure, temperature, and velocity of the gas exiting the fan. All right, so if you think about it, what would be the only difference is a bypass ratio difference. In terms of computation, what are the things that we need to compute, or what are the things that we need to solve, is will really uh, change only near low pressure turbine. So until high pressure turbine, there is going to be no change compared to the uh, numerical that we saw. Um, Even though gearbox comes in between uh, fan and the low pressure compressor, until low pressure turbine, there is no change in the numerical. So uh, you can think about it why it is so, because see, you have bypass ratio increasing, but the m dot of it you will never take into account until you find what is the amount of work required to run the fan. Okay, the amount of work required to run the fan or drive the fan is going to depend on m dot of the m dot in the fan. Okay, or bypass ratio, and that bypass ratio comes only during the computation of low pressure turbine. It does not even come in the computation of high pressure turbine, because high pressure turbine is driving only high pressure compressor. And currently we took all the pressure ratios same as whatever the numerical that we solved in the lectures. So it's not the solution is not going to differ until high pressure turbine. At the low pressure turbine, the work is different because your bypass ratio is different. Okay, so you will that's what you will observe now. First you have inlet, and inlet there is not much of a pressure rise you are going to get, because the engine is stationary, it is at the ground, m infinity is 0, and hence you will have P02 and T02 same as P infinity and T infinity. Okay, and next you have fan, and for fan again you will never use bypass ratio for computing pressures and temperatures across fan. Okay, uh, these are these doesn't depend on the extensive property in thermodynamic terms. Okay, these are intensive properties, it no need to know the extent of your system. So the m dot which is passing through the fan, it doesn't need necessary to find out, no need to find out P03 and T03, and that's why the change in bypass ratio effect will not come even in this place. Okay, um, so again your P03 by T P03 by T P02 is 1.36. So from there you can find P03, which is 137.8 kilopascal, and you have temperature T02 as 288.15 Kelvin, and fan we have some efficiency of the fan, and if you substitute all those things in here, you can find the temperature ratio. So I'm not wasting time here because this has been already solved. We will quickly go through what happens, just to give you an idea, just to quickly recap uh, what happens till high pressure turbine. Okay, so the temperature ratio across the fan is 1.102, and based on that you can find temperature at the exit of the fan, which is 317.55 Kelvin, same as what we got in the lecture. And then you have low pressure compressor. In the low pressure compressor, uh, you have pressure ratio of 2.47. So let's find out the pressure would be 340.37 kilopascal, and then similarly you can find the temperature ratios, because it has some efficiency also, compressor, and hence your temperature ratio would be 1.3388, and from there you can find temperature at the exit of the low pressure compressor to be 425.15 Kelvin. And then you have high pressure compressor, uh, and the pressure ratio is 12. So from there you can find the pressure, which will be uh, around 40.84 bar. Okay, same as we got in the lectures. And the temperature ratios, again the same formula you need to use to find the temperature ratio. The efficiency of the compressor is 87 percentage. Okay, and the temperature ratio comes out to be 2.1884, and the temperature will come out to be 930.41 Kelvin. So the gas or air which is exiting the high pressure compressor will be at 930.4 Kelvin. In the combustion chamber, we add fuel until it reaches 1600 Kelvin. So that is our goal in the combustor. So and combustor also has an efficiency of 96 percentage and also has a pressure loss of 3%. So from the pressure loss, you can easily find the P06, which is exit of the pressure at the exit of the combustion chamber, which will be around 39.6 bar at 3961.9 kilopascal. So it was entering at 40.84 bar, if you remember, and it leaves at 39.6 bar. So 3% pressure loss. And then how to find fuel air ratio? We will use energy balance, right? So the air enters at T05, so m dot core CPC T05, and we have fuel adding, and its energy is QR. So that those are the two things that we have here. And then while it is leaving, you have m dot core plus m dot f times CPH into T06, because turbine entry temperature is given 1600 Kelvin. So from here you can rearrange this equation, and you can substitute these values over here. You can check my check the numbers. It will be same as in the lectures, and you will get the fuel air ratio of 0.0228. Okay, it's the same fuel air ratio that we got. So basically nothing but the core stream is same as the as the problem, as a numerical given in the lecture. Only thing is bypass ratio has increased. That is going to basically increase your propulsive efficiency, because that's what theoretically, from the understanding of the gas turbine engines, we know by when the bypass ratio increases, the propulsive efficiency is going to increase. So here we are quantifying how much it is going to increase and what is the effect on thrust and TSFC. Okay. Again, HP turbine, there is no change. As I said, HP turbine just runs the HP compressor. All these are in the core stream. It doesn't run the fan. Okay. So the work is only to the HP compressor. And again, you can do energy balance. And the energy balance in the LHS of your equation that you have here is the work generated by the HP turbine. You can see CPH, and the RHS you can see it's a work required by the high pressure compressor. Okay, T05 minus T04, 5 minus 4. Now again you can substitute these numbers, and then you will end up having temperature at the exit of the high pressure turbine to be 1167.16 Kelvin. Okay, this is the temperature exiting the high pressure turbine. Now comes the real problem. Now you have oh, we need to yet compute the pressure. So the pressure again, we all know this formula coming from isentropic flow relations. We can substitute it, and you will end up having pressure at the exit of the high pressure turbine. Okay, which will be around 10.8 bar. Now we have LP turbine. In the problem, in the week, if you see, it was driving fan and low pressure compressor, right? So which is in the right hand side of the PPT. If you see, LP turbine is from process 6 to 7. Here in our case, the LP turbine is the process from 7 to 8. Okay, there is some station number difference, but basically the LP turbine drives fan and the compressor, you can see. But now the fan work, which basically depends on the bypass ratio, is now increased. Okay, and also the fan work uh, also has additional problems with because of gearbox we installed. We have additional gearbox efficiency, so which means we need to provide more work, or the LPT has to get more work out of the gas in order to drive the fan than whatever it was here, whatever it is here. Okay, one is due to the bypass ratio increase, the other reason is due to the gearbox efficiency. So these two things you need to take into account, so please be careful. uh, Let me know if you couldn't understand. So the energy balance would look same, the work done, work required for fan, work required for LPC, and that is the work that has to be generated by LPT. Okay, And this is where the things are a little bit different. You can see I have eta gearbox, okay, and that too in the denominator. Okay, so um, I hope why it is in the denominator. I hope you guys can understand. So this is an efficiency. I have to the work fan that I wrote here is the work that has to be generated to drive the fan. It's not the real work required for the fan. Okay, the real work required for the fan would be simply the numerator. Okay, this will be the real work required for the fan to run the fan. But since we have additional gearbox which loses some work, we have to generate more work to drive the fan. That's why you have additionally eta gp in the denominator. So please understand that. And then as usual, we have low pressure compressor CPC T04 minus T03, and which will be equal to 1 plus F CPH T07 minus T08. Okay, so T07 would be higher than T08 because these are all expansion process. That's why it's written like that. And you must have noticed that I already normalized this with uh, m dot core basically. That's why you have 1 plus beta and stuff like that. Okay, so this is the difference. So basically there's no difference. Only thing is this is the fan required in the two-spool turbofan engine. Here in addition you have to divide it by efficiency of gearbox because you have additional mechanical component which requires which has some efficiency. It is not 100% work transferring device. Okay. Um, so this will change your numbers a little bit, and also the beta is different. So here the beta was 9, you can note here the beta was 9, but here we are going to substitute it as 14. Okay, so this is the change, right? So because of gear turbofan we were able to go with a higher bypass ratio. Okay, and if you substitute all the other numbers, this is what you will get. So if you guys have calculator, you can quickly find out what would be the T08. So we can actually take a guess. So can you at least can you guys say whether the temperature that we have, what we get here, will it be lower than 823.12 Kelvin or will it be higher than 823.12 Kelvin? Let's see. You just take a guess. You don't need to give me exact numbers. You don't need to calculate also. But if you guys want to take a guess, will the temperature be lower than 823.12 Kelvin or will be higher? Any guesses? Lower, higher? Okay, we have mixed. Okay, nice. We have mixed response here. One, so Jasim is telling lower and Shubham is telling higher. Okay, so actually it should be lower. Okay, Jasim was right. Um, the reason is it's so you think about it like this. The work that has to be extracted from the turbine. So the work is extracted. So how the turbine generates work? Because of the expansion of air. So the air or gases which enters the turbine, the flow work is getting converted into the mechanical work in the turbine, right? So the if when you have high pressure and temperature, it will go to a lower pressure and temperature, and the difference between these two is what is driving you the turbine. So in the problem that we had in our lectures, it has a bypass ratio of 9, which means let's say I have 100 kg per second. um, I have to only generate work such that I pressurize only that 100 kg per second. Now our bypass ratio has increased to a higher value. It has increased from 9 to 14, right? So which means before I had, let's say for bypass ratio 9, you have 900 kg per second. For bypass ratio 14, you have 1400 kg per second. Now the fan pressure ratio was same. Okay. Now the amount of gases that you are pressurizing is different. So from 900 kg per second you have increased to 1400 kg per second. So which means I need to give more work to it, uh, more work to the fan. And if you want to give more work to the fan, then you have to generate more work from the turbine. And how does the turbine generates more work? It has to extract as much as work from the gases. And if it extracts as much as work from the gases get expanded to a very low pressure and temperature. Okay. So that is why ideally if you see, the exit temperature of the LP turbine will be lower than 823.12 Kelvin, because of one thing is bypass ratio, and the minor thing is you have additionally gearbox which has some efficiency, so you have to anyway give more work to it, right? So let's say even if you have same bypass ratio, even if you have 9 for both the engines, one that we solved which is a conventional turbofan engine, here you have gear turbofan engine but with efficiency of 0.98. So ideally in a conventional turbofan engine, let's say for example you are giving 100 kilowatt to the fan. Now here you will not be giving 100 kilowatt, instead you will be giving 100 by 0.98, which would be something like, um, which will be more than 100 kilowatt, right? 100 divided by 0.98, which will be 102 kilowatt, right? So more work you are giving to the fan in the gear turbofan for the same bypass ratio. And since you are giving more work, and how does that work come? You have to extract that work from the gases only. And if the inlet temperature and pressure of the gases is same for these two turbofan engines, the exit temperature should go even below, right? So that is the reason why it will be lower. And as Jasim said, you will be end up having 689.48 Kelvin. Okay, around 120 Kelvin difference that you will have. Okay, so you think in terms of energy. Now you are going to give more energy. So the core stream is same for both the turbofan engine. Even the conventional turbofan engine, even in the gear turbofan engine, core stream is same. But only thing is you are extracting more work from the turbine, and if you are extracting more work, temperature has to go lower. Okay. Um, all right. I think that must have resolved your problem. So now the temperature that we have is 690.48, 689.48 kelvins, around 690 Kelvin. Let's go forward. And then pressure, as I said, similar thing. Both pressure and temperature has to go down because we are taking more work out of it. So that is what you also see here. So you can see there is the equation wise they are same only station numbers are different. Okay. You can substitute these numbers, and at the end you will have lower pressure, as I said. So because we are taking more work out of it, so you will have to get low pressure and temperature compared to a conventional turbofan engine. And here the pressure and temperatures are really big. The differences are really big. So we have around like 130 Kelvin difference, and pressure is around 120 kilopascal difference. Okay. So this will ultimately change your nozzle performance also. Let's look at it. The next thing is turbine nozzle. In the turbine nozzle, this is what we solved, and the exit pressure was 115.54 kilopascal for the conventional turbofan engine, and we also solved that turbine nozzle is chocked. Now you see tailpipe we have no losses, so we'll leave it, and we have nozzle. The inlet pressure and temperature is around 100 kilopascal and 689.48 Kelvin. Now what happens is, again you need to find same methodology. You need to find critical pressure. So the choking condition will provide you the pressure ratios is anyway going to remain same 1.917, because we are not there is no change in gamma or eta. The pressure ratio depends on only gamma and eta, right, in the formula. You can look at this formula. So pressure ratio as such there is no change, but the P09, the critical pressure will be different because your P09 is different now. Before your inlet stagnation pressure for the turbine nozzle was 221.46 kilopascal. Now it is just simply 100 kilopascal. So that itself would have already given you uh, outside the pressure is 101.325, 101 kilopascal, and inside the stagnation pressure at the entry of the nozzle itself is lower, which means ideally this nozzle is unchocked, right? So, but anyway, to show using the relation, we can say the critical pressure would be something like 52.57 kilopascal, which is less than atmosphere. And since it's less than atmosphere, this nozzle is unchocked. So you can see that in that conventional turbofan, your nozzle was chocked, but here the nozzle is unchocked. Okay, so I hope this is also clear with everyone. If you have any problem, you can stop me in between. Now you have exit pressure to be 101.325 kilopascal. That is also given. And then you have temperature ratios and velocity we need to find. This temperature ratio and velocity that we solved for conventional turbofan engine is better different because we used chalked nozzle conditions. Now our case, you need to have different temperature ratio, different way of finding the temperature at the exit of the turbofan engine. So again, you can find using the isentropic flow relation. Nozzle is just a accelerating. Uh, it's an accelerating flow device. It's just going to expand your gas. So isentropic flow should work over there. So that is what you do here. Temperature ratios is around 0.9986, and this will be your exit temperature. So exit temperature as such you can compare. The exit temperature of the nozzle is also lower than the nozzle exit temperature for the conventional turbofan engine. Okay, since the exit temperature is also lower, in fact inlet pressure is also lower, the nozzle is unchocked compared to conventional turbofan engine. Ideally you will get lower exit velocity. So that's what you will see here. The exit velocity you have to calculate with this formula, 2 cp eta into t minus t, t09 minus t10, and if you calculate it, it will come out to be 132.53 meters per second. So basically you can compare the differences. So we just added a gearbox and we increased the bypass ratio, and just because of change in the work done by the turbine, you see the pressure at the exit of the nozzle in a gear turbofan engine has reduced to a very low value. The reason is your nozzle is unchocked. If it is chocked, it will be higher velocity. And the other thing is your nozzle inlet pressures are lower. Okay, those are the two reasons why your velocity at the exit of a nozzle is very less compared to the exit velocity of the turbine. Okay, so this will have an effect on the thrust, right? So if you have higher velocity, you are going to have higher thrust. If you have lower velocity, you are going to have lower thrust. But this nozzle is only core nozzle. uh, our turbofan equations have thrust from both core flow and also from bypass flow, right? So let's see how other things get affected. This is core nozzle. Now let's get into fan nozzle. In fan nozzle, again, there's no difference compared to whatever we solved in the lectures, because across the fan the pressure ratios are same as we solved in the lectures, and after the gas gets or air gets pressurized across the fan, it's going to expand in the nozzle. So again you can find the choking condition, it is going to be same as whatever we solved, and again you can find the critical pressure which will also be same, 70.15 kilopascal, which will be less than 101.325. Your fan nozzle is already unchocked. It was even in your numericals solved in the lectures. So again your exit pressure would be same as atmospheric pressure, and you can find the temperature ratios. Again the temperatures and velocity will be same compared to whatever we solve for conventional turbofan engine. You can also find the exit velocity of the nozzle. So only change that we saw here till now which can affect your performance is the exit velocity of the core nozzle, because exit velocity of fan nozzle is also same, coming out to be same as compared to conventional turbofan engine. Okay, so in gear turbofan engine, we took more work from the LP turbine, and hence other parameters reduced. And since it's reduced, you are not able to generate more energy out of it, more energy, more thrust out of it. Okay, so which means some amount of work that you see as a thrust is being used to run the turbine. So that's the so you that's how you think in terms of energy. Okay, so the next thing is you want to find area of the nozzle. So for the core flow, it's straightforward. Again, m dot core into 1 plus f, because fuel also is added, is P10, A10 and V10. And the changes here will be again P10 and D10 are different compared to the conventional turbofan engine. And also velocity is 132.53 Kelvin, which is different compared to uh, what we saw in the conventional turbofan engine. You can see they added 519.32 was meters per second was the conventional turbofan engine's exit velocity. Here it is 132, and because of this lower velocity, you will see a very high increase in area. So again, these are additional problems when you deal with gear turbofan engine. Your area of nozzle is big. Okay, now see, you have 0.477 was the conventional turbofan engine's area. Here you have 2.083. Okay, but anyway, since your bypass ratio has increased already, you have increased the turbine. Uh, what do you call turbine diameter, or gas turbine, the entire gas turbine engine size, because your bypass ratio has already increased. So um, anyway, we have to deal with the bigger uh, things now. And similarly for bypass flow, again you have for bypass flow, only difference is you have beta. This beta is no more 9, it is 14 now. Okay, so that's the difference. And if you do that calculation, your again area of the bypass nozzle will be 7.47, which is higher than the area of the fan nozzle that we saw in the conventional turbofan engine. Again, bypass ratio has increased, that's the reason. Okay, now the important guy, the thrust. So what do you guys guess? So let's try again a guess game. Do you think the net thrust that we produced from the gear turbofan engine, because of reduction in velocity that we saw in the what do you call core nozzle, do you think the thrust will be lesser than uh, the thrust that we calculated in the conventional turbofan engine? What do you guys think? Or so you can also say it cannot be predicted because there are other things. So if so, what are the other things that you will consider? So I hope you guys understand my question. So the thrust that we generate from the gear turbofan, will it be lower than the conventional turbofan that we saw in the lecture? If it is lower, why? If it will be higher, then what would be the reasons? Or if you are saying it is unpredictable, then you can say what are the factors that makes it unpredictable. So this is where it gets interesting now. So we have solved multiple all these what do you call thermodynamics relations that we used, everything. At the end of the day, we want thrust, we want TSFC. So how these are going to get affected is my question. Are you guys typing or? looks like you guys are thinking too much. So, okay, let me give you some hints. So, you think about like this. So, from conventional turbofan engine to gear turbofan engine, what has changed, right? Initially, what did we change? Bypass ratio has changed. So, bypass ratio has increased from 9 to 14, right? So, that's a huge jump, around like 50%, more than 50% increase in bypass ratio, which means more m dot. Okay, more m dot. That is the first thing you should remember. So more m dot means more thrust. Okay, so that is one, uh, what do you call, one point that you need to consider. So you have increased your mass flow rate. If you increase the mass flow rate, your thrust is going to increase, and this relation is almost linear. Okay, you can also see from this equation, m dot core times something that we are adding, and m dot fan times something that we are adding, right? So when you increase that m dot, you have, uh, you are going to get different thrust. So now from in the gear turbofan you have larger m dot. So ideally you should get higher thrust. But what also has happened is, your velocity V10, although V11 remains same, your V10 has reduced to a very low value from 513 or from 519. I'm not sure what was it. I guess, yeah, 519.32 meters per second. It has reduced to simply 130 or 170 meters per second, right? So there is a, like, you can say 2 to 3 times reduction in velocity of the core nozzle, ex- reduction in the exit velocity of the core nozzle. But you also see almost like 1.5 times increase in the mass flow rate. Okay. Now, based on these are two counteracting forces for your thrust. So one, bypass ratio increase is going to increase your thrust, but velocity decrease is going to decrease your, uh, what do you call, the thrust, right? So let's see what happens now. If you substitute these again, what we have is all this, both core nozzle and the fan nozzle is chalked, right? And hence P infinity, T infinity will be 0, P10 minus P infinity, and P11 minus P infinity will be 0, right? Because P10 is equal to P infinity and P11 is also equal to P. So the area change effect is not coming in. So from the pressure, we are not getting any, since area also changed, that is also one of the thing you need to consider. Area also, A10 and A11 is also increased for gear turbofan. That also will contribute to your increase in thrust, right? But since pressures are same, so that contribution is going to be nothing. Now you have only mass flow rate contribution or the momentum contribution, and what you have here is, we have substituted these numbers. So you'll be surprised to see you will get a thrust of 455.01 kilonewton. Okay, so you can do calculations and you can check for yourself. The thrust that you got from a conventional turbofan engine is 360.56 kilonewton. So the thrust that you're getting now for the gear turbofan engine is 455.01. So there is a huge increase in thrust, although there is a reduction in nozzle velocity. If you design your turbine, or if you design your engine in such a way that your nozzle exit velocity is also uh, optimum, or you, let's say you chalk your nozzle, then you will get even more thrust. Okay, so that is something you can design, but this that is a separate topic. Here, compared to conventional turbofan engine, we added a gearbox, and because of that we were able to increase our bypass ratio. And since we were able to increase our bypass ratio, we were able to get more thrust. That's the simple explanation. uh, so 138 times 9 times 225.83 is much lower than 138 times 14 times 225.83. Okay, so from 9 to 14, that increase is actually leading to very high increase in the thrust. Now, another important component, the whole point of is to reduce the TSFC, thrust specific fuel consumption. Let's see what happens to it. Now our thrust has increased, but our fuel ratio never changed, right? We saw till the low pressure turbine, sorry, till the high pressure turbine, exit of the high pressure turbine, there is no parameter change. Only after the exit of the high pressure turbine, you have low pressure turbine which is running, which is taking a lot of work and stuff like that. Until high pressure turbine is, so in the combustion chamber you are adding fuel and the fuel air ratio was same 0.0228, and the core stream we kept to be same 138 kg per second, and hence uh, from 360 you have increased to 455, so obviously you have reduced specific fuel consumption. So that is the advantage of this gear turbofan engine. uh, you are able to get lower thrust specific fuel consumption, so which was almost like we got 0.0069 grams per Newton second. However, in conventional turbofan engine, you have 0.0087 grams per Newton second. Okay. All right. And then we also have thermal efficiency. Um, in thermal efficiency, you are adding same amount of fuel, and what you have is a little bit change in your kinetic energy that is leaving your what do you call leaving your engine, but also increase in the thrust. So these are two uh, counteracting forces which might balance. For example, so what I'm trying to say is your thrust over here has increased, but our V, so anyway, the thrust component is not going to come because V infinity is 0. Our engine is in ground. So this component is going to go away. So increase in thrust is not affecting your thermal efficiency. So the second thing is that you have is your V infinity, or sorry, V10 core nozzle. This has reduced. Okay, so numerator has reduced, so thermal efficiency should reduce. Okay, but this m dot fan now over here, this has increased, right? Because your beta has increased from 9 to 14, it has increased. So these are counteracting things, so which might lead to um, increase or decrease based on its effect. So ultimately, for this thermal efficiency calculation, it lead to almost same thermal efficiency. You can see there is a slightest decrease in thermal efficiency of gear turbofan engine, which was around 37.33 percentage, while the conventional turbofan was 37.48 percentage. But anyway, we got good TSFC, so we are all interested in TSFC, right? Let's put everything in perspective. So this is the comparison that I have here. So this will be the without gearbox. This is with beta equal to 9, and here you have with gearbox but beta equal to 40. Okay, so here you have the gearbox. Here you don't have such thing, and so what you see here is the exit velocity of the core nozzle has reduced. I'm just summarizing what and all happened. It has reduced like around 75%. It has reduced. And the exit area of the core nozzle has increased 336.7%, which means like 3 to 3.4 times increase in the nozzle exit area. And fan nozzle is also 55% increase in the fan nozzle exit area. And the thrust is 26% increase, and TSFC 20% decrease. Okay, so this is how they were able to reduce the fuel consumption. And if you reduce the fuel consumption and you develop such an engine, if you install it in aircraft, you can reduce the air fare, like or the flight fare. Okay, so that's why nowadays all the engines are almost gear turbofan engines. Most of the commercial aircrafts are and also high bypass ratio engines. So we were able to go to high bypass ratio because of the gearbox. Okay, and the thermal efficiency, there's a minor change in thermal efficiency. That is what that those are the insights that we get from this problem. Um, So one important understanding that you take from this is you should not compare a turbofan engine, a conventional turbofan engine and gear turbofan engine when they have same bypass ratio. If you have same bypass ratio, your gear turbofan will obviously have will perform poor. Okay, because of additional components, additional mechanical efficiencies that you have here, and all this. Otherwise, there's no difference between those two. Additional gearbox will include additional efficiency thing inside your system. However, if your gear turbofan, if you have already reached aerodynamically efficient design for a conventional turbofan engine, for a given bypass ratio, and if you want to go further and increase your bypass ratio, then you install a gear turbofan engine and then you compare those two engines. Okay, for the same bypass ratio you should not compare. However, you should compare for a different bypass ratio. Okay, but same core mass flow or core stream conditions. Okay, so and then only you will be able to see the clear advantages of gear turbofan engine. Otherwise, there is no really an advantage of gear turbofan engine. So this is some a topic which usually everyone gets confused because uh, you know because of this additional complexity. Okay, I hope you are able to follow and you are able to really understand and appreciate the technology behind the gear turbofan engine based on this problem. And I think this will also be helpful for your week 7 numericals. All right. If you have any questions, you can ask. This is the question I have for today, and it's done. So I will be here for another 1 hour or so in this call. So if you have any questions, you can feel free to ask me. If not, we will meet again in the next week, week 8. Okay. Thanks, Shubham and Jason, for joining. I hope to see you in next week also. Please feel free to ask me if you have any doubts, both regarding this question and also the, in general, the lecture. If you have any doubts, you can ask. Thank you, Shubham. Sure, Shubham. We'll meet next week. Good night. Oh, okay. No problem. You take your time, go through the lectures, and we will discuss. Good night, Shubham. Bye bye.